Welcome everyone to the Mini-Science for the McGill University Bicentennial. McGill University is located on the traditional territory of the Haudenosaunee and the Anishinaabe nations. McGill recognizes, honors, and respects these nations as the traditional stewards of the lands and the waters on which we work, play, listen to music, interact with each other, and exchange information. Our speaker for this evening will be introduced by the student ambassador, Christina-Rose Papagiannis. After the presentation, the other student ambassador, Maxwell Gentili-Morin, will moderate the Q&A directly with the speaker in one of the new McGill laboratories. Live stream coming to you tonight. Christina, let us know who's speaking.
Hello, everyone, and welcome to Dr. Marcelo Wanderley's presentation, Shaping the Future of Music. So, who is your speaker today? Dr. Marcelo Wanderley graduated in electrical engineering at the Federal University of Paraná in Brazil. He holds a master's degree in engineering from the Federal University of Santa Catarina, also in Brazil, and a PhD from the Université Pierre et Marie Curie in France. Today, Dr. Wanderley is a professor of music technology at McGill University and the international chair at INRIA, the International Institute for Research in Digital Science and Technology. He's a member of Computer Music Journal Editorial Advisory Board and a senior member of the ACM, the Association for Computing Machinery, and a senior member of the IEEE, the Institute of Electrical and Electronics Engineers. Dr. Wanderley has co-edited the book, Trends and Gestural Controls of Music in 2000, co-authored the textbook, New Digital Musical Instruments, Control and Interaction Beyond the Keyboard in 2006, and chaired the 2003 International Conference of New Interfaces for Musical Expression. His research interests include the design and evaluation of digital musical instruments and the analysis of performer movements. Dr. Wanderley came from a family of engineers, but always wanted to work with music. Now working as an interdisciplinary professor of both subjects, Dr. Wanderley studies how technology changed the way we interact with music and how technology has now democratized music. Many people today listen to music exclusively through some digital device, phones, tablets, or computers. In the last few decades, digital technology has impacted how we compose, perform, record, distribute, and even listen to music. Digital technology has also allowed for completely novel musical styles and instruments to appear. In his talk, Dr. Wanderley, drawing on examples from his interdisciplinary research in music technology, will discuss how computing technology invites us to interact with music differently and speculate how technology can shape the future of music. We hope you enjoy his presentation. During the presentation, feel free to submit your questions to the URL in the YouTube description box. And now, let's hand it over to Dr. Marcelo Wanderley.
Thank you, Christina. Thank you, Ingrid. And thanks for the invitation to be here and speak to you about the future of music, or the way I see the future of music. Alors, bonsoir. Je suis très content d'être là, justement, pour essayer de parler un peu de comment je vois l'avenir de la musique et surtout la question de l'interdisciplinarité. Alors, j'espère, c'est la direction dont nous travaillons ici, c'est justement d'essayer d'aller au-delà d'un domaine spécifique et de voir la question de l'interdisciplinarité entre musique, science et technologie. C'est un peu l'idée du CARMIT, du centre. Je vais discuter de ça un peu plus en détail pendant les slides. Mais la présentation sera en anglais. Vous êtes le bienvenu pour écrire des questions en français, si vous voulez. Je peux les répondre en français ou en anglais ou en portugais, puisqu'on y est. So thank you again for the invitation. And as mentioned by Christina, I'm a professor in music technology. But actually, my background is electrical engineering. And I studied electrical engineering, master's in electrical engineering, PhD in technology, actually. But I always wanted to work with sound and music. And actually, that happened. Actually, I'm happy to be, for 20 years already, a professor of music technology. But being an engineer on the Faculty of Music, on the Schulich School of Music, means a lot of the research, or most of the research I do, is related to interdisciplinarity. So I work with technology, engineering, or computer science. But everything I do, basically, with my students in my research laboratory is applied to sound and to music. My main research interests are digital musical instruments. So instruments that are musical instruments that use computers or computing technology to generate sounds. And another main interest is the interaction between performers and instruments. So acoustic instruments or digital instruments, how skilled performers actually manage to express themselves using technology or even acoustic instruments. What is this detailed interaction between a highly skilled performer and their instrument? So let's take a look on, I mentioned digital musical instruments. I will talk a lot more about digital musical instruments during this talk. Let's take a look on one example. That's Andrew Stewart, professor at Lethbridge now. This was during his doctorate in composition here at McGill, and he plays the T-Stick by Joe Mallock. So the T-Stick is a tube. It's a tube of various lengths. I mean, you have T-Sticks, I can show you later during the questions, at 1 meter length or 2 meters length. So it's a family of interfaces. And they sense different types of actions or gestures, so you can move them in space, you can touch them at different positions, etc. But the whole question then is, how do we move from something that is sensitive, let's say, to gestures, to an instrument, something that you can perform and express yourself? So this talk, we'll start by talking why music. So show one slide here about the impact of music, and I think this is it's kind of eye-opening. We take sometimes music for granted, but music is extremely important and to a lot of people. Then I will go over 3 examples, research examples of music and digital technology. 3 different projects showing the use of technology to understand acoustic performances, to help neuroscientists look at what's going on in musical performances, and actually to create instruments for beginners. Then at the second half of this talk round, I will talk about new infrastructure at Kermit. And actually these are 2 cutting-edge research laboratories that we actually were able to get grants to fund these spaces. And one is the space I am here, it's the Performance Research Lab. The other one is across the window there, is the Multimedia room. And I'll explain why this new infrastructure, they are cutting edge, they're top world infrastructures for the study of music performance, interaction in music, and music with technology. And I'll wrap up with an example of musical use of technology. That's a project of a PhD student of mine, Eduardo Menezes, and with a duo of classical guitarists in the new MMR. So it will be a video presenting that. So music, the impact of music. Actually, music involves, in Canada, thousands of people, worldwide, millions. 35,000 people are musicians or singers in Canada, 4,200 are conductors, composers, and arrangers. That's 40,000 people directly involved with music professionally. Music is a big business. So for instance, the digital music sales revenue in Canada, it's more than $500 million. That's the digital music sales revenue. So mostly streaming. It's enormous. If you see the economic impact, then the impact on the lives of people who work on music. And of course, music impacts millions of people, even if they don't necessarily work with music. 93% of Canadians listen to music, 96% of millennials. And 53% of music consumers listen to music through their smartphones. And actually that's 79% of millennials. So again, this shows first, music is a serious thing. It's not just, oh, we do music for pleasure, whatever, great, it has to be, and it's amazing when we do. But it's also a very serious business, a very serious career. And research in music is pretty serious too. Right? So there's very important engineering, computer science, neuroscience, psychology done on music, physics, etc. but also the impact of technology. And you can see that this, a lot of the music we hear today and the examples you will hear today in this talk come to you through technology. We learn to play music somehow through technology. We listen, we appreciate, we compose, etc. So the role of technology is also major. So tremendous impact in music composition, performance, recording, distribution, listening. And that was already before artificial intelligence. So that's even more dramatic impact. And if you have tried recommendation engines and whatever, you see what I'm talking about. It's amazing how these engines actually are getting to understand what we like, actually sometimes even better than we do. So there's so many possibilities, of course, drawbacks too, that it's not always a panacea, right? It's always good and bad about, but the impact is there. But for me, what's interesting in my research is that digital technology has allowed for novel musical styles, but also musical instruments. So we can make musics that we couldn't before, right? So thanks to sound synthesis, thanks to sampling, thanks to computing power these days, that actually your watch probably is more powerful than lots of computers we had 20 years ago. And let me show one example here and then a second example of a piece that's done with thanks to technology. So that's the beginning of Événements by Christian Bouchard, an acoustic composer. And actually, that's another example now. It's me playing with synthesizers at home, some software synthesizer. But every sound you hear basically is done with technology. There is no acoustic instruments involved on the next one. Right. So again, all these styles, and there's a lot of people who actually enjoy, but also make a living out of playing in clubs and playing, having bands and recording, etc. Thanks to technology, again, DJing, etc., etc. So what is it's interesting about these instruments is on the left there you see a clarinet, on the right you see that tube that Andrew was playing on the first video there. And that's the T-stick, right? So a digital musical instrument on the right is a clarinet, obviously, an acoustic music instrument. So an acoustic instrument, actually, both the interaction where the musician plays the instrument and the sound generation happen at the same time, at the same place. And that's even true for the guitar, the electric guitar, even if you have the amplifier farther away, but it's still the strings with which you interact and vibrate. And this vibration is picked up by the pickups, etc., etc. So it's all integrated, and they function according to acoustic principles, right? So columns of air vibrate at certain frequencies, etc., etc. Right? Digital instruments on the other side there of the picture, there's a separation between the interface where you interact, for instance, the tube, and the sound generation. The sound generation might be a laptop computer, might be your watch, might be any computing device, or even a synthesizer. It probably has a computer anyway. So the question then is, there is no more physical connection, there's no more obvious connection, natural connection between what you do and what you hear, right? So the same gesture can have completely different examples, completely different outcomes, right? So then the question is how to design and play these instruments if all the possibilities are open. So let me show another example of someone playing. It's Fernando Rocha playing the T-stick. It's a different T-stick, it's a bit larger, but it's the same principle. You can touch it at different places, you can shake it, you can move it in space, and it's sensitive to its orientation, to how hard you touch, etc. So it's a composition by D. Andrew Stewart, again, the performer of the first video. And actually, what's happening in this video, Fernando is a professor at Universidade Federal de Minas Gerais in Brazil now, but he was a doctoral student in performance here at McGill. And this is part of his doctoral recital. So he's actually performing to be evaluated as a performer to get a doctorate. So this is a composition he practiced enormously. So let's see how he interprets this. But again, think of this as a performance, not as a demonstration of a technical device. So again, the interface is pretty much the same. It's bigger in this case, but the functioning is basically the same. So it's the same type of messages, computer messages to the synthesizer, to the computer, but the sounds and the way to interact are very different. And that can be shown in this diagram as a kind of summary of what a digital musical instrument is. So in the center there you have the input device or the interface, so where the sensors are and where you can actually basically interact, hit, shake, move in space. You have the computer on the right. And the computer actually, there will be several ways of generating sounds in computers. And actually this comes from the 50s already. There's research in sound synthesis in computers is 1950s, end of 50s. So there's dozens of ways of creating sounds, and you can choose the one you prefer. And then there's a very important part in between the interface and the computer, that's the mapping. So the interface gives me electric signals, so digital signals. Computer receives digital signals, but how I connect the digital signal from my accelerometer, for instance, the sensor measuring shaking, to the sound synthesis input, for instance, FM synthesis or name it, it's mapping, so that's open. Again, there is no more acoustics or physical properties to say this variable needs to be connected to that variable, etc. So it's an open problem. So it's, again, an opportunity and a problem, actually. So why things work or don't, what's the role of learning, etc. So to give you another example of a digital musical instrument, imagine, obviously, these interfaces do not need to be similar to anything we know. They don't need to have similar sizes as clarinets or guitars or whatever. So what would be the sound of someone performing a bicycle wheel? Would you imagine, you have a bicycle wheel, you want to do an instrument, how would you go to have this bicycle wheel generating sounds, controls for sounds? And that's an example now. That's a video by Elliot Sr., was a master's student in my lab. And Elliot was research on his master's was exactly using these devices that actually have mechanical properties. So he had a spring that he would actuate in different ways, bicycle wheels, and actually the bicycle wheel is turning around this axis he's holding in his hand. And then because he's moving in different directions, he gets this precession effect that actually depends on the direction he moves. He has forces being either helping him move or pushing him not to move in that direction. And that's actually how a gyroscope works. So that's why gyro tire. So the point here is how to design this bicycle wheel. So the bicycle wheel is there, right? So which sensors to use to measure speed of rotation, inclination, etc. But also how to connect this to sounds. And you can see that in this video there, he's actually playing arpeggios. So the notes are already predefined and they change according to the inclination. He's not playing every single note as we would do with acoustic instruments. So you cannot just do a gesture on the clarinet and have 20 notes coming out one after the other, right? So you have to every moment go and interact, shape the sounds, right? Articulate sounds, etc. With computer instruments, you don't need necessarily to do that anymore. You can have actually some of these parameters already predefined, and that's what he did there. So the choice of notes are from a set, but they are already created. The articulation of these notes are already there, right? So it depends on how he moves. He will play these notes. So he's more in between a performer and a conductor in a sense, where some of the parameters are already being defined, right? But that's obviously one way. It doesn't need at all to be like this, and that's a second video where he plays the same interface, same sensors, etc., same signals sent to the computer, but in a very different way. So in this case, actually, he's in yet another level of interaction. He's interacting with the material. There's a sound recording there, and he's moving in as a recording ahead of of a device reading the sound file at any moment, like a cursor, he's moving in and out. So it's even a much lower level than an instrument. He's not playing notes there, he's really playing inside whatever this sound it is. So you can see again, digital musical instruments allow you to interact with sounds in vastly different ways. This is a major point about technology, allowing you this freedom to play sounds. So let's start looking at some examples now of using technology for different cases. I mentioned 3 of them. So the first is the analysis of performances with acoustic instruments. So a violin, and the idea is measuring the expert interaction between the bow, I mean the violinist playing the bow, and the string, the instrument, the violin. Right? So how do I do this? Well, in this case, we went for a technology that's used in many different fields. It's called motion capture. It's the work of Erwin Schondervat, who was a visiting PhD researcher in my lab. So motion capture basically is attaching markers, typically it can be sensors or other devices, to bodies or to one's body. And actually, there is a system tracking the position of these markers, typically the 3D position of the markers. In this case, these markers are passive reflectors that reflect infrared light from multiple cameras in the space. And then multiple cameras, you can reconstruct the 3D position of each of these markers thanks to the multiple views of the cameras. And there's many other technologies. There's electromagnetic, there's active infrared, etc., etc. There's many examples of using music, but that's mostly used in animation, in movies, also for rehabilitation, etc. So obviously we place markers also on the bow, so we can then reconstruct the bow as a solid and the violin as another solid. But to measure, for instance, the pressure that he's applying, the force of the hair on the string, we needed extra sensors. So that's not so good to do with visual because the displacement is minor. So we implemented a sensor that was developed at IRCAM first using strain gauges. So the idea is that the deformation of this hair, thanks to the force, can be measured. So then you estimate the force, you calibrate, etc. So suppose we capture all these extremely fine details like sub-millimeter movements, etc. What do we do with this? Well, we could create new performances, animate performances. That's what people do in games, for instance, or movies, right? In our case, what we want is to visualize these very high quality movements. And that's Lambert Chen performing on a violin. It's the Chrysler Allegro. And you will see on the top panel there, you see the violin seen from the top. You see the bow, and the red dot there is the frog of the bow. And you see the frog, the orientation of the frog. That's the blue and inside the circle. On the lower one here on the left, you see basically the 4 strings of the violin and the bow at each of the strings. So when the person is playing one string, it stays inside one of the colors, the A in this case, or when it moves across strings, you will see patterns. And these patterns are very, very interesting and they have been identified long ago. But it's nice to see this, and actually it's a kind of representation of the quality of the performance. So it's amazingly precise, actually, very repeatable. On the top right, you have the bow force. So again, we use the sensor to measure exactly how many newtons are applied at any moment. And the bottom right there, you have a phase diagram between inclination and bow velocity, right? And the idea then is you can see these patterns. Phase diagrams are great for seeing repetitive movements. So let's see this excerpt of the Chrysler Allegro, but at the detail level that you will not see by if you're listening to a high-level violinist performing in a concert. Right, and again, this is amazing because obviously allows you to see this level of detail. Again, this is not visible necessarily, but allows us, for instance, to compare different performance, and different high-level violinists might play the piece slightly different or with their own static preferences, right? So you can quantify these differences by looking at this level of detail. Furthermore, of course, you can use this for learning or pedagogy. For instance, someone learning to play this piece, you can start by looking on how regular the movements are and eventually try to match them or to compare them or to have some sort of metrics to evaluate how this is improving, for instance, with different training sessions, etc. So that was the first project. The second project is actually a collaboration with neuroscientists, and they came to my lab 2005, I guess, and say, well, you design musical instruments, digital musical instruments. Can you design instruments to be played inside the MRI scanner? I said, sure, why not? And book, what's an MRI scanner? Ooh. Right, so if you have already been inside or you know about an MRI scanner, basically that's a very specific environment, is a very complicated machinery there that has a lot of constraints. First is a space constraint. So you cannot just walk in the room where the scanner is with your instrument, sit somewhere and play. So the question is how to design these musical instruments that are actually working, that is, they generate sounds, but that can be played in MRI scanner. So they fit the space, but also they are safe to the performer. That was the master's and then PhD of my student Avram Hollinger, also an engineering student who had a master's and PhD in music technology. And that's a collaboration with Robert Sartori and Virginia Penhune from Brahms and Kermit. Brahms is the International Laboratory for Study of Brain and Music. And so this took 7-8 years in total, and we created a prototype of a small piano, so a small keyboard. It's not a piano, it's a piano keyboard, a few, 1 octave, a bit, and that actually can be played inside, so it's safe. It doesn't affect the measurements. Obviously, if you have an instrument that works, generates sounds, but it spoils, I mean, ruins your brain image that you are trying to capture, that doesn't help. And we created a cello, and the cello is the picture you can see of the cat there behind the drawing that led to the cello. And let's see a small video here, and that's Mélanie Segado. She is a cellist and was a PhD researcher in neurosciences. She's already finished. And she was also part of the project. So first thing you see, it's far from what you would expect a cellist to be doing when performing, right? I mean, I don't know many that perform lying down. The cello is also not what you expect as a cello, maybe an electric cello. So again, constraints on the environment. You don't want any magnetizable objects because actually can be safety, really serious safety issues, right? So we went again, I will explain this in the next video, but most is everything fiber optics. So let's take a look at a quick example video about the project. The question of MRI is that it's a very specific environment. It's an environment that has several constraints and mostly magnetic constraints. Our main challenge here was to create instruments that have materials that are non-magnetizable. So we had to rethink all these electronics and all these sensors.
So this is the first real cello prototype that anybody's developed in the world. We've been working on this for about 5 or 6 years.
So we went for optics. So most of everything we do is using light to sense position of fingers, to sense positions of keys, to sense, for instance, a position of a bow in space. So we had to design instruments, and this includes the electronics. So we had to design instruments that bypass or that don't use such materials, but also that don't have electronic circuits. So basically, we couldn't have electronic circuits and sensors, normal stuff that we would use for different projects, for instance, the tube, etc., inside the scanner, because again, these magnetic constraints. So all these circuits had to be in a different room, and everything inside the room where the measurements are done, that had to be everything optics and fiber optics, etc. So we could measure what was being played and position of the bow, etc., etc. So now, The last project, the Probasio project, is a collaboration actually with a former visiting PhD student, Felipe Calegaio from Brazil. And the idea is how to help people create their instruments. So how to easily, simply create functional prototypes of digital musical instruments, right? So example like this tube or another one. So again, collaboration, Felipe. Felipe is now a professor at University Federal do Pernambuco in Brazil, and it's a joint project with the IDMIL, my lab at McGill. So how do we go about this? So imagine you want to create an instrument. So if you already have knowledge on electronics, design, 3D printing, etc., you can just pretty much do it by yourself. That's great. I mean, there's several tools that are pretty user-friendly compared to the state-of-the-art 20 years ago. Arduino microcontrollers, sensors are becoming easier to use, and pretty much all digital, etc. But if you don't have that, if you don't want to spend time developing this, so how do we go with this? So our proposal is to start thinking about postures. How would you like to play your instrument? Would you like to hold it as a guitar? Would you like to hold it as a kind of tambourine or pandeiro? That's a Brazilian instrument that actually comes from Italy, the original ones. Basically, as I was told, or a flute or a guitar, different, put it in your lap, sit on it, etc. So once you chose your posture, think about the controls you want to have. So do you want to move something, crank it? Do you want to bang it? Do you want to play strings? Do you want to use bows, blow into it, etc., etc.? So once you do this, you can then create your own instrument by imagining postures and controls. And for instance, there, the red lines there, you have a guitar style posture with a crank and keys, and you have a guitar with a crank. If you have the same posture, but you use, instead of the crank and the keys, you use the pad and the pandeiro, right? You can have a pandeiro guitar with a slide, etc., etc. You can sit like a John, etc. So this is great because allow you to imagine your instrument. So you can basically start and think about how do I go with my instrument. Of course, it doesn't stop there, right? It has to be more than just, okay, that's the paper, that's my instrument. So the next step is we have a prototyping environment that is ready for you to test your paper idea, posture, etc., into your instrument. And this is what you can see there in this image. Basically, you have a base, that's the 3x3 support there, where you can put your blocks. Once you put these blocks in the base, the blocks are immediately functional. Once they start playing, right, you can then manipulate sounds, either excite sounds or modify sounds. So that's what Felipe is doing there. You can obviously move, add new blocks, take blocks, and play around with this. So that was the first version of the device, and I'm in control. And this is the second version of the tool. And this now, what is different now in this version is actually we use 3D printing actually for everything. It's much easier to reproduce, to replicate, but the principle is the same. Blocks that connect to bases. And once this is connected, you can then have the sounds immediately coming. So you test your idea immediately from the instrument. So I can answer questions. I even have an example here. I didn't switch it on, but you can see the 3D printing part. So that was 3 different projects where I'm showing where technology can help us or can open up new directions. Right? Now, the second part of this talk will be about this new infrastructure. So I'm talking about Kermit. Kermit is this horizontal structure across universities, departments, etc. So it's McGill, Université de Montréal, Université de Sherbrooke, and ETS. And departments from all these places, plus researchers from other institutions too, in Quebec, and collaborators from around the world. And the whole idea is interdisciplinary research. So people will come from electrical engineering, music technology, philosophy, psychology, neurosciences, computer science, name it. And they will work in projects together. So the second example you saw there with the neuroscience research, the instruments for neuroscience research, was an example done at Kermit and Brahms. Kermit has already six state-of-the-art laboratories on the last floor of the Elizabeth Wirth Music Building. And now this infrastructure actually allows us to have 2 new cutting-edge research laboratories funded by amazing grants from the Canadian Foundation for Innovation, the CFI, and the government of Quebec that I co-wrote when I was the PI, when I was the director of Kermit, actually. And we were lucky that these grants were approved. And the first lab is the Performance Research Laboratory, this room. And the second one is the Multimedia room, that room, behind the speaker. So this is the part of the -2 level, so the underground level of this building, the new music building, Elizabeth Wirth. And the blue part is the room we are, the Pearl Performance Research Lab. The green one is the MMR. And you can see the difference already in volumes and space, right? The Pearl is a 75 around square meters room. The MMR is a 422 square meter room, right? Much bigger. I will give more details about them. So the first grant was a small medium grant of $1 million for renovations of the space and equipment. So what we want to do is to create this performance research and rapid prototyping laboratory. So to do exactly Probatio style tools. So built with 3D printers, laser cutters, etc., and prototyping material, we can build instruments and immediately test. Then we can bring them to the lab and see how musicians will take these instruments and actually decide on performance techniques, decide on how to play them. Right? So this is major. Understanding this process, how people create these techniques with instruments that don't have necessarily predefined sounds. Right, so the idea is to do longitudinal studies, so to go over time and see over weeks, etc., months, how people develop this performance, how can they teach these techniques to others, etc. So that's the room here. Basically, renovations, acoustic treatment, dome of speakers, etc. So lots of equipment. Right? So thanks also to Elizabeth Wirth for matching this grant for extra functionalities. And the multimedia room across here is much larger. It's $11 million grant, and it's a grant actually to create a performance hub between McGill and UDM. So basically the idea is it's a joint grant where we collaborate. It's 2 of the biggest music schools in Quebec, actually, and in Canada. And the idea is to create this facility for music students of obviously McGill and UDM, but also any music student or researcher interested in participating. Again, the idea of studying performances, either through recording, to concerts, to tests with technology, etc., to study 3D sound, so sound that is displayed anywhere. It's not only around you, but it can be in a 3D, in a semisphere, and immersive environments. Interaction between performers and ensembles. So for instance, how sections in an orchestra coordinate. Perception issues, how does sound integrate into perception, etc. Distributed musical performance, so you can have part of the orchestra in one place, part in another, and study the influence of delays, for instance, lag, or the types of feedback you give to musicians and how this impacts performance. And overall, performance involving technology. But it's also an amazing performance room just for acoustic performances, orchestras or ensembles or live, and we will see an example. So these are the 2 spaces. The left is the MMR before the renovation. So you can see the floor was not really up to speed. It was cinder block walls. We had curtains, etc. So the room was there, but we never had the funds to really complete this as a fully functional, cutting-edge, world-leading research laboratory. Right now, this is true. Second is Salle Côte Champagne, an amazing performance hall. And actually, they at UDM, they bought equipment to measure performance, microphones, cameras, etc., etc. So This is a video that I used. The simulation is we did when we were constructing, these renovations. And actually shows you, it's easier than piloting a drone to show up and down here. So I will explain a bit this room. This is a simulation of the new multimedia room. The multimedia room, the MMR, is a meta laboratory for the study of music performance, but also the application in science and technologies to sound and music. First, note here the volume of this room. This room has some 420 square meters of surface and 7,000 cubic meters of volume. So it's a very large room that allows to have either small ensembles and an audience or a full orchestra in music experiments and tests or performances. Then look at these characteristics of the rooms. For instance, the panels on the wall. You can see here there are two sizes of panels, and basically they are diffusers. Means panels that actually reflect sound in many directions so that the room sounds natural for performances. That was made specifically for this project by Kierkegaard and Associates. Then other characteristics of the room includes these banners that you can see here, vertical banners, and this curtain, the horizontal curtain on the bottom here. These banners and curtain can be actually deployed to change the acoustics of the room. So the room can be drier or more lively depending on the position of these banners and curtain. Apart from that, so that's mechanical changing of the acoustics, but we also have this sound system here. You see the loudspeakers. These are basically 62 loudspeakers from Meyer Sound in California. And they are placed in 3 different levels. And this system actually allows us to go further from the mechanical changes of the acoustics and have virtual acoustics. Simulate acoustics of another room, for instance, in this space. Another feature of this room is the trampoline that you can see here and the rigging system. So this basically is a short view of the simulation of the room, but actually if you have the opportunity to be here, it's exactly how it looks. Actually, you can see part of it now. And again, I would say chapeau au gouvernement du Québec, chapeau au CFI, à l'Université de Montréal et au McGill. Et bravo, c'est une des salles uniques au monde. Il y en a peut-être quelques-unes de plus, mais pas vraiment pour la musique, pas vraiment de cette taille, et surtout pas dédiée spécifiquement pour la recherche en musique. Ça, c'est vraiment une fierté, c'est génial ce qui se passe. C'est même incroyable des collègues qui viennent d'autres pays qui regardent, mais comment vous faites ça? Comment vous obtenez ça? Et ça pour moi, c'est très important, justement, c'est l'idée de faire, d'être excellent dans ce qu'on est très bon. Et grâce au CFI, grâce au gouvernement du Québec, nous y sommes. So that's again, thanks, enormous thanks to CFI and keep on doing this in the government of Quebec. It's major. So I'll try to go fast here. This, one of the issues of this room is that this room had to be an amazing room for acoustic performances, just an orchestra, just assembled, just one performer, but also with technology. So amplified music, synthesized music, noise, etc. So how do you go to design something that has to be good in multiple things? It's a casse-tête, it's a headache for designers. And one of the issues, we had to come up with our own sound diffusers. And this is actually designed by Kierkegaard and Associates in Chicago. And actually, basically, they came out with this format of the diffuser for us for this project here. But not only they have to design it, we have to test it. Because imagine there's hundreds, I don't remember how many exactly, 400, 600 panels in these walls there to make this room feel natural for performance. So then imagine if they start rattling when someone plays something, or there's noise, or if they have some resonance and you can hear this sound distortion on what you want, or enhancement of sounds that where you don't want them to be. So this was a lot of the research we did here once prototypes of these panels were done. And that's why CARMIT is exactly a research center, interdisciplinary on research in science, technology, or music. So we were happy to test ourselves with laser vibrometers, different types of acoustic techniques, measurement techniques, to see how good these panels. And actually, we had to redesign, change slightly the materials to eliminate certain issues with preliminary prototypes. This is a quick picture of the trampoline and the rigging system. So you can see it's a mesh structure that you can walk actually and place cameras, lights, microphones, anywhere you want in the room, basically, to do experiments or recordings. This is another major feature here. We had to redo a lot of the structure to hold, these metal structures to hold these panels in place. Imagine the weight of hundreds of panels. These panels are heavy themselves individually. So the room was not obviously designed for that. I mean, this came after the initial design. So this was all part of the renovation project. It's major. And this is a picture of the room pretty much the way it is today, except that in that picture is the floor was still not the final floor that is already there. So these two spaces are functional. They are minor details, and we got delayed, obviously, because of the pandemic. But in principle, the final deadline for everything fully working and available is December now. So it's minor details. And actually, concerts and recordings have already happened. And that's basically, I will conclude here with an example of these performances that happened here is Guitar Ami is a project by Eduardo Menezes, a PhD student in my lab, who's defending pretty soon. And the idea is augmenting the classical guitar, so the nylon acoustic guitar, with non-invasive, self-contained technologies. So the idea is to allow guitar players, classical guitar players, to perform sounds and modify the sound of the guitar in ways that they wouldn't be able just with acoustic, probably with their actions, with their gestures. Right? So we add electronics to the instrument to allow this signal processing, digital devices. But the important part there is that the guitar still has to be fully playable as an acoustic instrument. So what we add actually brings some extra options to the performers, but should not replace what the performers do with their instruments already. Otherwise, we would be losing enormous quality of, that's exactly what expert performance is about. Right, it's a collaboration between Eduardo and the Chiquiliti duo by Adam and Steve. So professional classical guitar players, right? And it's amazing that this was possible actually to use this technology in performances. And you will see examples, for instance, when Adam goes a bit lower with, backwards with his torso, you can see that actually that affects the distortion or actually the reverberation of the sound. That what he's playing. So there are some details, there are pedals, etc., with processing of the sounds. And you will see more details if you want on the full video. And let's take a look. It's part of the live at Kermit and recording on the renovated MMR. So Chiquiliti duo. So again, it's amazing for me as an engineer to see technology actually helping very high level musical performance and not just as a demonstration. You know, it's amazing to be able to create prototypes and devices that people can play with as fun. But it's also amazing to see when these technologies actually have the potential to be as acoustic instruments. And that's the goal of our research here. So to conclude, shaping the future, so the way I see the future, or the way I hope the future will be, is more and more the confluence of music, science, and technology. And this confluence opening up new opportunities to understand, create, experience, distribute music. And again, music is pretty serious. Music is major for a lot of people. Music can allow for high-level research, right? In engineering, in computer science, in physics, etc. So there's a lot of people involved in this and a lot of very high-quality research coming out and products coming out. So thanks to all of the people I didn't mention that participated to these grants. For instance, there's several people involved. And these people are world leaders on what they're doing too. Novel devices and environments have the potential to democratize access to music and to include diverse populations. For instance, we can imagine novel devices for people who actually do not have basic control of or basic functions that basically we would have ourselves or normal population. So for instance, there's systems for tracking eye position, right? So that people with major physical impairments can control with only their eyes, can generate sounds and music. One is developed in collaboration in my lab, the AUMI system. And for me, what's very important too is the new opportunity for a new generation of interdisciplinary researchers and musicians. And this is major. It's actually not only using and developing this research and publishing and being known internationally, whatever, but also training a new generation of people that are open-minded, people who have a very strong background in one topic, engineering, music, computer science, psychology, but they are aware of others, the importance of the approaches in other fields. Right? So this is major. It's creating people that can think outside the box, outside boundaries of structure, vertical structures that we know that are very important in certain cases. But interdisciplinary research can bring a lot to research, and I hope we'll do more and more of this in the future. So thank you very much for listening, and I'm ready for questions. So Maxwell. And we are 2 meters away.
Yes.
You have a microphone, yes? Don't step on your tablet. And thank you again for the invitation to do this talk, right, and to the organizers. So Maxwell, fire up.
So we good?
Fire away.
Thank you for the presentation. So let's move on to the Q&A. Throughout the process, I've been seeing that a couple have come in. More in detail, 4. So the first one, he was wondering if the future of music will be all digital.
Aha, where's my crystal ball? No, definitely. Well, who am I to say yes or no? But basically, I don't believe it will be all digital. Of course, digital, personally, I think it will take more and more space. And it's just because there is an opportunity to take space, not necessarily because it's forcefully better or it's more convenient digital. And that allows a lot of people to have access where they wouldn't have access. But I hope, and it's obvious for me at least, that a lot of the musical practice we have today will continue the way they are. And actually, perhaps digital technology will perhaps help people learn instruments or understand how sound is made with acoustic instruments too. But it's obvious for me at least that lots of the music we do will continue to be done just because culturally they are essential and very important to many people, to me included.
So next one is from Daryl, or not Daryl, but Adrian, actually.
Oh,
Sorry.
what?
He's a musician that's working with numerous granular synthesis applications on on the iPad. And this new digital technology makes it possible to dissect music waveforms into minuscule grains and reassemble them into new, never before heard tones, timbres, textures, and full soundscapes. His question is then, does digital granular music synthesis have the potential to revolutionize the evolution of music, or is it simply another fad destined for obscurity?
Good point. I would say neither nor. First, granular synthesis is not so new, actually. I think Curtis Rhodes was one of the first to develop granular synthesis. I think it was late 60s, early 70s, maybe late 70s. So it's already there. There's several related synthesis topics that are there also for decades, called concatenative synthesis, etc., that you can play with these atoms and create larger sounds and etc. So it is very widely used, granular synthesis. Will it replace others? No. Will it become the main one? Probably not. It will be yet another. It is yet another tool, as you have a tool chest, and you might prefer a certain hammer to another sledgehammer to do something, right? Because of your own preference or because of the task you want to do, because of your knowledge, right? But I think it's a powerful tool, as many others. Physical models, good physical models eliminate signal modes. Physical models, those were not in sound synthesis. Physical models try to model the vibration structures of materials, so the propagation of sound. So you have equations, typically, that actually allow you to simulate exactly how it would sound if it was a real thing. Signal models is you try to simulate the frequencies, the result of the sounds, or abstract synthesis like frequency modulation. You modulate two tones. None ever replaced another, right? And I don't think it will happen with... but it's not a fad, actually, and it has happened for decades. So enjoy. I mean, if you like it, that's what you are proficient at and what helps you express yourself. That's your tool. That's great.
All right. So the third question is, they're asking, is digital music/sound used in artificial intelligence as an input for industry processes in healthcare or manufacturing?
I don't know myself, but I guess yes, because again, there's a lot of people using digital sounds, and artificial intelligence again is there, and it's in a lot of applications and tools we already use every single day. So it will only grow bigger, actually. And there was a Mini-Science, the first talk on this series this year was about future of artificial intelligence, actually. So. Probably, yes. I'm not aware personally. It's one of the tools I use. I'm not a researcher specialized in artificial intelligence. But yes, I've seen systems for composition, systems for analysis. In my own research, we use that for helping to define the mapping strategy, for analysis of performance movements. So it's a great tool to crunch a bunch of data and find out styles or find out expertise on large database of data.
Where do you see the future of music technology going in 5 to 10 years about? There's another question.
Where would you like to place your bet, right? Devices, it's basically, I think there will be more and more devices. These devices will be more and more integrated, I hope, and intelligent. And hopefully, in my view, we would better interact with devices and stop having issues with Zoom and interfaces that stop working and do this and then slides moving in and out, etc., etc. So there's so much to do there. For instance, on the way we interact with these machines, so that the machines try to actually put themselves in our place. It's called effective computing, right? Can we display effect? Can the machines understand effect? And can they display effect? So can we have this higher level communication that's not just like, oh, his Mini is doing this, he's saying that, it means that. So gesture recognition, postures, all this information is extremely important. And sometimes machines do not take this into account. So it's very important to get better ways of interacting with machines. And eventually, including self-driving cars, if you know, right? It's very important to improve this. And I hope one of the directions of digital music will be that it will be more natural to interact with
That's a
tools
perfect
that we have
answer.
today that potentially you can if you're very skilled, but it's not at the level of everybody.
I have to interrupt and tell you my device has told me that we have to finish, and I get to officially thank you all. First of all, to our speaker, we gift all our speakers with special things from the Red Path Museum. You will be receiving, Marcelo, a booklet about the mineral collections. You will receive a wonderful stereoscopic postcard. This was created digitally. It took the photographer 3 solid days of positioning himself with a camera in front of this dinosaur. And you will get a little analog notepad made from recycled McGill paper, so you can scratch away on it. Here you see even leftovers from, our scientific illustration course. Thank you, Maxwell.
Thank you very much.
For the Q&A. Thank you, Christina, for the introduction. Thank you for all the backup team. That's people at McGill Multimedia.
Daryl.
And your team, Marcelo, at your lab. I don't know if we can see who they are. If there's any way we can
Daryl,
give a hand to everyone today. And then I just have to let you know that we'll see you back here all together. Hi, Daryl. Thanks again, everyone. Hope to see you all in about a month, September 9th, 6 o'clock, live streaming with Andy Gonzalez, his mini-science title, Charting a Course to Global Sustainability in the 21st Century. Have a great month. Bye, everyone.